Okay, and we're good. So last time we did a very quick introduction on proofs. Just so how quick, in my other class we started statements and we could only finish statements, right? But we went through like a bunch of proof techniques. So we're on moving lightning fast because what I spoke about is important for us to know, but technically there's no room in our syllabus for it. But I still thought it would be good if I just take a couple classes to run through it really quickly to sort of help you guys along the way, so that later on when we start just doing proofs left and right, you're not completely lost. The nice thing about the linear algebra proofs, the one that we'll be doing, they're not going to be super complicated proofs in general, but the ideas are important. So we spoke about what statements were. These are mathematical declarative sentences that you can prove to be true or false, but not both. So that's an exclusive or in terms of truth value. We spoke about tautologies, which are statements that are always true, contradictions, statements that are always false. We also spoke about how to combine statements like with and or, and P implies Q, and then we actually did some proof techniques. So we did direct proof. Let's just start there, a quick review of the proof techniques. So we're still on, not in any real thing yet. We're still on lecture 00. Just recall some proof techniques. To prove P implies Q. What was the first technique? We looked at the direct proof. And you remember what we did there? How would you describe a direct proof? Assume P, show Q is true as a consequence. Right, so that was a direct proof. We also had the indirect proof, or proof by contrapositive. And how do you prove something using the contrapositive? What do you start assuming?
Assume not Q.
Assuming not Q, meaning the opposite of Q happens. This is the negation of the statement Q, which we also spoke about. We spoke about how to negate and or, and how to negate quantifiers. So that's just the opposite statement of Q. And then you have to show not P is true as a consequence. We spoke about proof by contradiction. What did you have to assume for contradiction?
Assume the hypothesis and the opposite of your conclusion, and then come to some
P and not Q, and then you have to show a contradiction arises. So a mathematical statement that is always going to be false, you have to show that that happens if you assume P and not Q. Right? And this could be a contradiction from anywhere in all of mathematics. It doesn't even have to do specifically with what you're talking about. But if you make this assumption and something breaks, 1 + 1 now equals 3 because of this assumption, even if you were talking about matrices, that is good enough for a proof by contradiction. Okay? We also looked at induction. Okay? And this was when we had a statement. This is when we have a statement that depends on n, where n was a positive integer. Right, so this is a statement depending on n. And how did we go about proving that?
P1 is true.
Show that it's true for the first guy, show that P1 is true. Then
Assume true for arbitrary n.
assume P of n true for arbitrary n. A lot of textbooks will actually use a different variable here. They're like, prove that P of k is true and show k + 1. And I'm going to mention something as to why some textbooks go that extra step. But for now, it's the same as saying it's true for some arbitrary n. So you're not making the assumption it works for all n. You're just saying, so let's suppose it works for some particular n, and then you have to show what?
P of
You have to show P implies P of n plus 1. And by the way, this in and of itself is proven using one of the previous techniques, right? It's an implication that you have to end up proving. Okay? Now, it's very important that you kind of know these techniques of how to actually write a proof, how one is supposed to begin, because odds are, if you begin in any other kind of way, it's going to be wrong. So let's talk about that. How not to start a proof. Sometimes it's good to know what not to do as well as what to do. Besides stating some definition, that's just not a definition, that's wrong. Here's probably the single biggest mistake that I see students make. This is very wrong. Okay? You cannot start by assuming Q. This is called begging the question. It is a very common error, at least for first-time students in proofs making. And basically, it is assuming what you need to prove. Right? So for example, if I ask you to prove, if I ask you to prove that x squared is even, implies that x is even, and you start the proof, assume x is even, I stop reading and you get a 0. You have already messed up beyond repair. The moment you assume the thing that you need to prove, that is called begging the question. You cannot do that, right? That is not any proof technique. There's no proof technique that we've looked at that starts by assume Q, right? So you make that error, it's a very big error. It's called begging the question. One reason why it's an error is because you're guaranteed to be able to prove whatever you want by doing that. Why? We looked at the truth table for P implies Q, right? You'll notice that in every case where Q was true, the implication was true. Meaning, if you assume Q is true, and you make only logical deductions, it's literally impossible for you to prove whether that implication is false. You always get that it's true, because you kind of assumed it's true in the beginning. So any other logical inference you make will continue to maintain that it is true. So if you start out with a sentence that is wrong, you assume the conclusion, you'll end up proving that it's true, which should not be the case, right? This is called begging the question. You cannot assume what you want to prove. So if you need to prove P implies Q, and you start out by saying, assume Q, blah, 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 literally nothing you say matters. It is not a right proof. It is completely wrong in one of the greatest possible ways. And that kind of goes for pretty much any of these proof techniques. So it would also be wrong to assume, for example, not P. To start out a proof by assume not P, right? Where are you going to go with that, right? Because if you assume not P, what will be happening, right? So if you want to prove x is even implies x squared is even implies x is even, and you start out by assuming x squared is odd, what are you doing, right? You would assume that the antecedent is a false statement, right? Which guarantees that your implication will be proven true. So again, you can end up proving something that's true that should be false, right? So that's why when I listed these different proof techniques, I told you this is the first step. These are the things you're allowed to assume. Do not assume anything else. especially Q. Like this is a particular one that's very bad, in very bad taste, to assume that. That's called begging the question. You never assume what you need to prove.
I'm confused how that's different from assuming P of n is true for arbitrary n.
Because this is a statement, because this is a for all statement. And this that you assumed is a for some statement.
Even though it's arbitrary, it's still just for a single. Okay.
Yeah, for some arbitrary, right?
But if it's arbitrary, it could be any of the n's.
No, well, I said for some arbitrary.
Okay.
It's not for any arbitrary thing you want to pick. Let's say you find an arbitrary guy, like some obscure number. Okay, it's true for the 13,576 choice, right? That's not going to do it. Right. So this is a statement about every single n value. At some point, you're going to assume it's true for some particular n value. And then you want to prove if it's true for some particular n, it's true for the next one. And that, combined with the fact that it's true for the first one, would cascade into the fact that it's true for all of them.
Why don't you have to prove that it's true for that particular n?
Hmm?
Why do you assume it's true for that n?
Because the base case, you try for the base case, and then if you want to do other cases, and you see if it works, so then you just suppose it's true for that case. And then you're going to somehow conclude that.
So you want to say, why don't we prove it's true for this?
Yeah.
Well, you would end up with an infinite regress, right? Because if you always come up with a case, you never get to a position where you never get to a starting point if you keep saying, I have to prove it's true for some n. Because you literally have to end up doing an infinite number of proofs,
Okay.
right? So you just assume it's going to work for someone, and then it will work for the next one, right? And that prevents you from going in this loop. Because then someone can always argue, well, why did you prove it's true for that n? What if we started here? You know, you don't want that argument. Yeah.
I have a question on that.
Also, there's something called strong form induction, which we're not going to get too much into, where you might have to prove several cases in the beginning in order to end up being able to say this general case. But we won't really have to worry about that too much, unless you're in 308.
I've seen for like some proofs in the 308 textbook where it's like, for like a question like that, x squared is even implies x is even, right? That one.
Hmm?
Say that I wanted to tackle that as with a direct proof. So then it's two cases, right, where x could be either odd or even. And then if
Sure, that would be a proof by cases, which I'm going to talk about.
yeah, so I have a question about, so like say that if it's, so the case is that x is even, then we're finished, right? And then,
No,
well for that one particular.
because still starting off with the x squared is still a problem. Because you'd still have to end up dealing with a radical, right? We kind of showed that if you attack this with a direct proof, you're going to get a radical in there that you have to deal with that you're not going to be
Oh no, like
sure.
what if it's like I'm using some outside fact that I know that the
Well, you have to
integer.
use some outside fact, then sure.
No, like say that like because there's like a domain in the background there, right? It's like x is some integer.
Yeah, this was an integer. Yeah.
Yeah. So then, what if I say that okay? So then integer can either be even or odd. So then I can say case one, it's even. And
Yes,
then you're
but
done.
you end up with x squared is even, and then you can say we're done if it's even.
For like one.
Is that
case.
what you're saying?
Yeah. So then if I wanted to do that by cases, right? So then that would mean that x would have to be either even or odd.
Yeah. But this still forces you to say this. And how do you deal with that?
No. I meant like just from the idea of like what x is. So it's like it's gonna be like let x be an integer. So then I'm saying that okay, the x can either be even or odd.
Sure.
So then we say case one that it's even, then it's done. If it's even, right? And then if it's odd,
What does that do with the square?
No, so I have a question about that. So if I'm saying that x is odd, for that part of that subcase, would I end up trying to prove some kind of, would I end up at a contradiction to do that by direct proof?
No.
So like,
And by the way, what you're kind of doing is,
I see the book doing like these special tricks where it's like they're secretly using like a contradiction within the direct proof, and they're supposed. I'll show you.
oh yeah, you can do proofs inside of
Yeah.
proofs. That's okay. But again, still starting off how you said, you would end up at an impasse. For this particular example, at least, you'd end up at an impasse. You won't, to start out by assuming this is odd or even is not going to really get you anywhere. Unless you have some other super high level number theoretical theorem in the background, in which case, if you already have that, this is probably not even something you'd be proving in the first place. Because odds are you would have to prove this to be able to get to that level in the first place. Okay, so it's important that you also know the different proof techniques, but know how you should begin them. Because if you start off wrong, if you start off on the wrong foot, everything is wrong. So let's talk a little bit more about, I want to do two major topics, proof by cases and also proof or disproof and existence proof. So basically 3 different ideas. Then we'll sort of bring this to the land of functions, which will ultimately be able to segue into the land of matrices, and then we'll be able to start linear algebra. Okay, so here's another technique. Proof by cases. So sometimes we are able, of course sometimes, not all the time, but sometimes we are able to break up a statement into a finite number of cases that describe all possible situations, that together describe all possible situations. Proving a general claim by proving all the possible cases is called a proof by cases. And of course, even within a case, you can have cases. These are called, therefore, subcases. So you can have cases, and then within a case, you have a bunch of subcases. But sometimes it's the best that you can do with all the information you have. So that's called a proof by cases. Commonly, it might start out like this, similar to what Young was saying. If you want to prove P, you can start by saying either P is true or not, right? In other words, you can literally break up any mathematical statement into 2 groups. Either the statement you want to prove is true, or the statement you want to prove is not true. This is basically you're assuming P and not P, right? And why you can do that and it doesn't violate anything we've spoken about Can anyone not in my 308 class tell me why is this okay to say? Yeah?
Shouldn't that maybe be like P or not P? If it's either P, it's
True or not, yes. Yes, but why is that okay for me to say?
True.
Huh?
Because I mean that is true. True or false is
Because it's a tautology.
Yeah.
So it's like me just saying something that's obviously always true. Okay, sure. Right? So in other words, so for example, you might be in a case where it's talking about proving something for all integers, and you can say, well, the integer is either even or it's not. And you can start the proof by saying that. because yeah, that's obviously true. That will always be true. There's nothing wrong with saying that because that's a tautology. Because if you have P, not P, and you have P or not P, if you do the truth table for that, this is true, that's false, this is false, that's true, this would always be a true statement to say. So you can always just randomly say this tautology, and at the beginning you're wondering, what's the use of saying something that everyone obviously knows is true all the time? It can give you an advantage in making the proof. So it helps you to break things into two cases. And oftentimes when you do this, one case you don't have to do because you're like, either it's true or not. If it's true, you literally don't have to do anything because it's true. Then you only end up dealing with the case where it's not true. And it allows you to kind of do something that's illegal in that you can prove a statement by assuming that it's not true and deal with that case. And then show that that's impossible. So that's called a proof by cases. So let me give you an example of proof by cases. Prove that if n is an integer, then n squared plus n is even. Now I'm going to prove this by cases, but I'm also going to show you another way to prove it, but the cases is what I really want to emphasize. Okay. Now you look at a statement like that, and you see that this is the statement, if P then Q, right? But both statements are kind of problematic to work with, right? So if n is an integer, okay, assuming that is me assuming what? Right? And if n squared plus n is even. We know that this is going to be a problem because whether or not I assume that's even or odd, I'm going to end up with a radical and it's not going to be a nice thing to start with. Assuming that n is just some integer is also not something, as well as if you want to start by assuming that's not an integer, okay, then it could be an infinite number of any other things. So when you're faced with that, you can just decide to, okay, let's break it up by cases. Let's figure out a way to split up the integers that makes it more manageable to work with. And we already know about odd and even, so that would be something we would do. So here, we can do a direct proof. Assume n is an integer. And then like, okay, what do we do now? Then, there are two cases. N is even, or n is odd. I've broken up this general statement to two specific statements that cover all possibilities. If you are an integer, you are either even or odd. So if I prove that this is even in this case, and prove that this is even in that case, I would have ultimately proved that it's even in every case, and therefore the statement in general is true. So case one, n is even. So deal with that case by itself. If n is even, what's true?
N squared is even? N equals 2k?
Sure, but by the definition, n equals 2k for some k. Easy. Then, oh, I see why you said n squared is even. You're going to be using, I see why you said that, but I don't want to use that because I didn't actually tell you guys that factor. Then n squared plus n would have to be what? Now just plug this in here. It's 4k squared, plug it in here, 2k. That means that I can factor the 2. This is an integer, and so n squared plus n is even. Then I do the next case, case 2. If n is odd, then n is equal to 2k plus 1 for some integer k. Then n squared plus n would be equal to, I'm going to square this, plus that. And I'd be able to factor out a 2 here. So this is 4k squared, that's 2k squared. This would be 4k plus 2k, which is 6k, so that's 2 times 3k's. 1 plus 1 is 2, factor out of 2, I get a plus 1. This is an integer, and so n squared plus n is even again. And then you can say, you could end the proof right here, but you could also say, they'd usually end by something like, so we see the claim holds in all cases. So we start with a general statement. Both of the statements were kind of hard to get my hands on, so what I decided to do was just take the general case, break it up into smaller subcases that are more manageable. So for any integer, that's a very overwhelming statement to say, so let's break it up, evens and odds. And depending on the question, it might be expedient for you to break it up some other way, but in this case it was good to break it up in terms of evens and odds because I ultimately wanted to prove something about being even. And so even and odd covers all integers, so it covers all cases. If it's even, this guy's even. If it's odd, he's still even, therefore for everybody he's even. And this is an example of a proof by cases. Any questions? Now it turns out that there are other things you can prove with odd and even integers, but this isn't really a number theory class, so I'm not going to tell you. But there are things that say, like if you multiply an even times an even, you get an even. If you multiply an even times an odd, you get an even. Add 2 evens, you get an even. Add 2 odds, you get an even. Add an even and an odd, you get an odd. And so you can even use little things like that to get through it. You can also prove that if 2 integers are consecutive, then it means that one of them have to be even, one of them have to be odd. There are all these assumptions. So there's actually another way you could prove something like this. Note that if you take n squared plus n, you can literally factor that. And these guys are consecutive. So 1 is even. And then you can say since an even integer times any integer is even, n squared plus n is even. So that's a little bit more of a high level proof. You'd consider what you're using here to be lemmas, because I'm making some statements here that generally you would have to justify at some earlier point. But the point is, for a single proof, there's more than one way to skin a cat. There are more than one correct logical ways. And as long as you're obeying all the rules, what you can do is verifiable and consistent with a truth table. You can know that you're not being subjective, you're being very logical, very objective about the truth that you're proving, and you can get to the right way. But there's multiple ways to prove things in general. If you look up the proof of Pythagoras' theorem, you can find websites where there are like 100 of them, right? So there are a lot of facts that you can prove in multiple ways, but just make sure you're doing something that's right. So that covers proof by cases. And one of the first, I don't remember if it's the first, one of the first big theorems that we're going to look at, which talk about the solutions to a system of equations, I'm going to use a proof by cases to prove it. It turns out that for any system of equations, there's a finite number of possibilities for for what its solution space looks like, and a proof by cases is one of the easiest ways to see that. Yeah.
I don't know if you said this or not, but did you say that you can use that as a proof instead of proof by cases?
Yeah, it's an alternative.
Okay.
But it is an alternative that would only sort of be accepted if at some point this was made clear. Right? some point you'd probably have to
Yeah.
show that, oh, an even times another integer is even. That's something that you'd have to justify.
Okay.
So there are sometimes, something like that is what you would call a lemma to a proof. So before that, you'd prove what you call a lemma, right? Which is a useful fact that you can use within another proof to help you with something. So you can have a theorem, which is a big proof, a very general overarching statement that's very important for you to prove. But then you can use little mini proofs to help you within that proof. And then in your math books, if you will find the word corollary, right? And basically you want to think of that as a consequence of some theorem. So here's this big theorem that I want to prove. I use a smaller proof to help me prove that. But once we know this is true, here are all these nice consequences. We call them corollaries. Yeah, that's a proof by cases. Let's talk about disproving. In other words, proving that something is false. Which can often be a very important thing, right? Because sometimes you stumble on some sort of issue that's in your way, and you're not exactly sure. You want to use it, but you're not sure if it's true or false, right? It's not every time that everything is obviously true or false. And so sometimes you have to prove that, okay, this is actually false, so I can't use that fact, right? And if you prove that something is wrong, that it's wrong to say it, you said you've disproved the thing, right? So there are some important ideas here. You cannot disprove a general by giving an example. In fact, you can't do that by giving any finite amount of examples. Okay, so that's something that's important to know. Also a common mistake with students, there are times where I might say, oh, prove that this is true for matrices. And the student will actually give me a proof in which they specifically use a 2x2 matrix. Like I never told you a 2x2 matrix, I said prove it's true for matrices. The fact that you singled out a particular kind of matrix and proved it for that does not prove the general statement. You cannot prove something general by just telling me a finite number of examples. There are many cases in which that's just downright wrong to say, right? So you can't just tell me, oh, you know, well, 3 is prime and 5 is prime and 7 is prime. Those are 3 odd integers in a row. Maybe all odd integers are prime. No, because then the next, you end up with 9, which is the next one, and now it's false, right? So just because you can find a few things that match the claim that you care about does not mean you can assume it will cover it in general. And there are many things that we had conjectures for way back when we didn't have the technology to verify them, that now with supercomputers and more computational power, we're like, oh, it turns out that that was wrong. So now we've satisfied the conjecture, right? Because then a supercomputer figured out, oh no, after the 1,000th billionth time, it breaks down, right? But as a human being, you're never going to get to the 1,000 billionth case, right? So it's very important that you never say something general or universal just by saying, oh, I found a few examples where this worked. It's not something you can do, and it can be wrong and get you into a lot of trouble.
Sorry to clarify, you said you cannot prove or disprove a general
You cannot disprove.
Okay.
Well, you can't also not prove either.
Okay.
But disprove you can, technically. You cannot... Oh no, it should be prove. Yeah, so I was saying prove, but I wrote disprove. However, you can disprove a general statement using an example. And when you make such an example, we call it a counterexample. Sort of like a counter argument to your argument. Right? So if someone makes a claim, oh, all prime numbers are odd, you can just pick one example where that doesn't work. Here's 2. 2 is prime, it's not odd, right? Then you've made them wrong, right? This is because we've actually shown that the negation of a universal statement is their exists statement, right? So you can show that there is some example and it can negate a for all, a claim about for all. So that's called a counterexample, right? So you can use a finite number of examples to disprove a general claim, but you can't use a finite number of examples to prove some sort of general claim. There's only one case. There's only one case really where you can use an example to prove a general claim. And that's if the claim is about the existence of something, right? So if there's a general claim that says somewhere in all the real numbers there's a real number that does this thing, if you can find that example, you've proven that claim is true, right? Right? So these are claims about the existence of some object, right? So if I say somewhere in the universe there exists this object, you can actually prove I'm right by providing an example of that object. Existence claims are super important because sometimes when you want to prove a statement that you don't know whether it's true or false in the first place, you don't want to, a lot of times when mathematicians work on a problem, it takes years of their life, right? So you do not want to start out spending years of your life just to find out that, yeah, I got nothing. And, you know, I spent the last 10 years working on this problem, then this new kid who just got into PhD school showed an example that it was wrong. It's not the kind of thing you want to sort of end up with. So existence claims are very useful because they kind of give you confidence to say, oh, the answer is out there somewhere. No one's ever found an example of it, but we can sort of know that it's out there somewhere, right? And so there are a lot of things that this can give us confidence to go down a certain rabbit hole that we otherwise wouldn't have gone down, right? So I don't know if any of you have taken differential equations. Right? So like in differential equations, there's the very important theorem called the existence and uniqueness theorem, right? Which basically tells you if you have a differential equation that looks like this form, there's definitely a solution out there, right? And because you can get to a solution in multiple ways, it's basically the one that says, no matter what you do, if you get to this answer, you can stop looking. There is no other answer. It's a unique answer, right? So there's no need to keep looking, right? You can know that when you found it, it's there, it's unique. So you know it's out there, and you know that when you find it, that's the only one there is. So claims like that are very important, right? So you have to know how to use and not use examples, right? You can't prove something in general by using examples, but you can disprove something. So that's an important idea. Okay? So in general, if I ask you to prove something, and you only give me a finite number of examples, or you only give me proof, a more general mistake here is to prove it for a subset of all the possible cases. So if I ask you, prove that this is true for all integers, but you only prove that it's true for even integers, you haven't answered the question. What about the odd ones? You know what I mean? So it's very important that you have that distinction. Whenever something is asked in general, make sure you prove it in general, not with examples. Okay? So Unless I tell you that I want you to prove something for 2 by 2 matrices, don't show me a proof that only shows 2 by 2 matrices, right? I'll have to tell you we're only considering that in order for you to go there. That's pretty much what we want to talk about with proofs and just some pitfalls that you may or may not fall into. Let's actually bring things back to functions for a little bit. Preliminaries part 2. Let's relook at functions, some special kinds of functions. I'm going to illustrate some things for you using some examples. So nothing here can be taken to be in general, but we will prove that you can take them to in the general case later on. But it's just to sort of segue into what we'll be doing. Because throughout the semester we're going to be doing things, and sometimes you're like, what's the point? Why did we have to define it that way? I want you to understand what is the background and the context in which we're going to do things. So we're going to talk about matrices, and I'll be able to tell you things you can do with matrices. And here's a definition for when you multiply a matrix. And you're going to be like, why is that the definition? And this is why. Right? So let's consider these functions. Let's just keep it like Rn to Rm, where m and n will vary. So I think I have 3 functions. We're going to do a bunch of things with them, and we're actually going to segue into matrices from that. So let's say here's a function. It's p is a function. It goes from R2 to R2. Right? So that's the domain. It takes 2-dimensional vectors, and it outputs 2-dimensional vectors in the following way. Plug in the vector xy, the output is going to be ax plus by, comma, cx plus dy. Right? So where a, b, c are constants. Fixed constants. Right? So if you plug in the point 1, comma 2, it's going to take a plus 2b and c plus 2d, and that's the vector it's going to output. So that's my first function. So it's a function that goes from a 2-dimensional space to a 2-dimensional space. My second function also goes from a 2-dimensional space to a 2-dimensional space. Q goes from R2 to R2. Where q of xy has a very similar definition, but for some fixed constants, I think I just went along with the alphabet here. Ex plus fy, comma, ef, g, h, turning it into an English class. So e, f, g, h in R, and they're fixed. Here's my third function, r of xy. I'm going to call a function that goes from R2, but now the output is in R3. So here, it plugs in a vector, and the output is the coordinate E, F, G, H, I, J, K, N, N. Okay? So here are some functions. So Calc 3 is a prereq for this class, so hopefully this isn't too scary to anyone. So these, you can think of them as vector functions, where the domain space is R2 for all of them. The codomain is R2 for these two, but it's R3 for that one. So you plug in a 2-dimensional vector, and the output is a 3-dimensional vector. Okay, so these are my functions. We're going to do some operations with these functions. A. tell me what is P plus Q, which I'll shorten them as P and Q from now on. How do you add functions? How do you add vectors?
Components.
You add component-wise, right? So you add the x components together. This is ax plus by plus ex plus fy, comma, you add the y components together. Cx plus dy plus gx plus hy. And now within the component, we have just a bunch of real numbers. So we can actually simplify that a little bit by factoring, right? So this is a plus e times x plus b plus f times y. And this would be c plus g times x plus d plus h times y. So, okay, that's cool. Not so bad yet. What about p plus r? How would you add p and r?
Can you?
You tell me.
Yes.
What would it be?
Do we assume that there's like a third component for that?
There is no third component. There's one comma.
You just said zeros though?
Yeah. You can.
It's
You can't. It's undefined.
Yeah.
You can't add a two-dimensional vector to a three-dimensional vector. Another concept you learned from Calc 3, because it just doesn't make sense. Like a three-dimensional creature cannot be imagined by a two-dimensional creature. The information is just not there. Even if you say the information is 0, it still can't tell you anything. And later on we'll see why more. Because assuming that, for example, oh, let's just throw in a coordinate 0, you actually change things drastically. We're going to show that in some future examples. But for now, you can't add the 2D coordinate to a 3D coordinate because this guy requires a third dimension of information. This guy has no third dimension of information, right? So it does not make sense to mix them together, right? It's like writing a program in two completely different incompatible programming languages. If you throw them all into one compiling system, it's like, what the hell is going on, right? I can't match the two. The informations just don't line up. So it turns out that adding these two is undefined. The dimensions don't match, right? It turns out dimensions have to match for you to be able to add something. Let's look at something else. Let's look at P composed with R. Remember how to do a composition of functions? What does P composed with R mean?
P of R of x, y.
Right, P, and you plug in R of x, y. Okay, what is that? This means P, and I'm going to plug in what? What is that?
Is it undefined?
Undefined. Why is it undefined?
It has no y.
P takes two-dimensional things as input, right? It can only process 2 dimensions of information. You cannot give it 3 dimensions of information. It cannot conceptualize that. You can't plug that function into that one because, again, the dimensions don't work well together. What about the other way, though? What if I look at R of P?
What is that? Sorry, what is that notation again? Between
Composition.
composition.
So it's like if you have a function f of x and you have another function g of x, then you define f of g of x to be f where the output of g is plugged in as the input of f. This is a composition of functions.
Okay.
So you could say something like f of x equals x plus 2, and your g of x equals x squared plus 1. And so what this means is that if you take f of g, that would be you take the g, you plug it inside the f. Right, so this creates a new function. And I'll talk about the significance of this function in a little bit. but just understand the concept of plugging one to the
Is
other.
that just f of g of x? Is
That's
that-
called f of g of x.
Oh, okay.
Or just f of g, or f composed with g. There are many ways to say it, but you should be aware of what the symbol means.
Got it. Thank you.
Okay, so what is r of p? Is that even possible? This means r, and I'm going to plug in the output of p, right? Which is ax plus by, comma, cx plus dy. Is that possible?
Yes.
Yeah, this is a two-dimensional vector. R does take two-dimensional vectors. It takes something with two components. I just plug something in with two components. So it should be able to work. I should be able to get some sort of output in R3 from this composition. So in other words, I'm going to replace this entire thing with x, and then replace this entire thing with y in the definition of my function. So I'm going to have I times ax plus by plus j times cx plus dy, comma, k times ax plus by plus l times cx plus dy, comma, m times ax plus by plus n times cx plus dy. Let's group all these together, probably skip a few steps. How many x's do we have here? How many y's do we have? Comma, how many x's do we have? How many y's do we have? How many x's do we have? How many y's do we have? So, who are all my x's here? IA, over AI, coming to take over, and JC plus JC. How many y's?
BI,
BI plus
DJ, JD.
or DJ, JD, here's doctor. So this is AK plus CL. For the y's, that would be BK plus DL. And for this guy, it would be AM plus CN, and this would be BM plus DN. Right? So now for emphasis here, we can actually draw some pictures. What is the point of a composition of a function? Okay, so let's say here we have a domain space R2, there's another domain space R2, there's another domain space here, another, ultimately the codomain R3. And what I just showed here, for example, is that P is a function that goes from R2 to R2. So P is going to go here and output something there, right? That's what the function P is going to do. Then what's going to happen is I'm going to take that input, that output of P, and plug it in as the input of R, because R goes from R2 to R3. So it's going to take that element and move him over here. R is going to do that. Right? Now, what is the significance of R of P? What is that function doing?
Taking R2 to R3.
Where does that go from, and where does that spit out?
From the first to
From the very first one all the way to the very last one, that's the function R of P. In other words, a composition of function is a way of cutting out the middleman. You can have a chain of events to get from A to B, but sometimes you just want to simplify the entire process. Tell me a streamlined way to get from the first thing to the last thing. You've created a composition of functions. That's what a composition function is for. That's why it's just a more efficient way to describe a process, right? Remember, a function is just a rule that tells you how to assign things, right? A composition is just a simplification of that rule if the rule has multiple steps, okay? But at every given step, the output of one part of the rule has to be able to be digested into the input of the other part of the rule, right? Otherwise, you break the chain, right? So in order for the composition to work, the individual functions have to work nicely together. In other words, the output dimensions of one function must be the same as the input dimensions of another function. Otherwise, the chain breaks.
I have a feeling this is very common in like programming or whatever.
Very common in a lot of ways. Linear algebra is super applicable to programming. But, yeah. I'm afraid you are wondering, what does this have to do with matrices? He's like, okay, I see what you're doing, but what does this have to do with matrices? What does this have to do with linear algebra? Like, why are you telling me these things about functions? Okay, we already know this from Calc 3. We never really mentioned any matrices in Calc 3. What's the point, Jamal? Okay, here's the point. Let's say I'm kind of lazy. And writing this out is super annoying because, you see, I even had to go to a second line. You know, I have to like write all these, like this, it's too much information. Let's use a notation that streamlines this information. Allows me to write it in a more compact form that's very understandable. So let's say I had p of xy. We knew that this was ax plus by, comma, cx plus dy. Right? For one, that row is too long. Let's write it as a column instead, you know, just because. And you know what? When writing it in that form, it's kind of obvious to me that the guys in the first column are attached to x's. The guys in the second columns are attached to y. So let's say that is assumed. Anything in the first column corresponds to an x coefficient. Anything in the second column corresponds to y coefficient. So really writing x's and y's, superfluous. Let's just write a, b, c, d. I know that the a and the c are coefficients of x. I know that the b and the d's are coefficients of y's. So I can end up writing, instead of writing this huge long sentence of things, I write a nice little compact rectangular array of numbers. Okay. In other words, the next function, q, how could I write that in a compact form? My q was, I don't remember what I said, ex plus fy, right? So that was e, f, g, h. Right? Also, I could rewrite my r function, where the first coordinate was I, j, k, l, m, n. Let's go over the operations we just did and rewrite them in this new notation.
Professor?
Yes.
That second line, do you still need the x and y vector
For what second line?
for a, b, c, d, the matrix?
No, I'm just showing you the process and how I'm creating this notation here.
Oh, okay.
So instead of thinking of it as one long sentence, just
Gotcha.
put each one underneath it. Look at a row vector as like a column vector. X's and Y's become superfluous in this arrangement because
okay.
it's clear that the first column is X and the second is Y, so let's not write them down. I'm lazy.
Okay.
And so with that method of compressing the notation for this function, my P would end up being this, my Q would end up being that, my R would end up being that. Huh?
Why is it 3 by 2?
I think so.
Oh, no, X, no, never mind.
Yeah, there are three components. This is what was before the first comma, this was what was after the second comma, this was after the third comma. I'm doing this. Let's look at the operations again. The first thing we tried to do was P plus Q, right? And what actually happened there? You remember that long sentence? You can compare it to what I'm about to write down. You'll notice that the x in the first coordinate was given by a plus e, was the coefficient of the x in the first coordinate. B plus f was the coefficient of the y in the first coordinate. C plus g is the coefficient of the x in the second coordinate. D plus H is the coefficient of the Y in the second coordinate. So it seems to me that with this notation, I can add things by sort of adding corresponding entries into this object. Okay, sort of like how you had to add corresponding components. By writing in this notation, and I say, let's add these two objects together, in the background I'm thinking of them as functions, even though they might not look like it right now, but in the background I'm thinking of them as functions, and I'm like, this has to be the definition. This has to be the way of adding these two objects. Yeah.
So just back to R, I mean, do we think of each row as like a set of basis vectors? Is that?
Yeah, but that's like in the second part of it. I'm going to deal with that in the
Okay,
second
alright.
part.
I was just confused because there was no z-axis, but that makes sense.
No, the z is this.
Right.
So you can think of this as the basis in the I direction, the base. Let's not use I because I'm using I. The
Okay.
basis in the X direction, the basis in the Y direction, the basis in the Z direction.
Okay.
But that's way beyond where we are right now. The point is, I can add these two objects. That definition is the only one that makes sense because I'm thinking of them as functions. This is how I add functions. So this has to be the way I add these guys because these guys are representatives of the function.
I got it.
Okay? So the definition of addition of these two objects, that's the only way to kind of define it to make sense if this is the interpretation I'm putting on those objects. So that's the way that makes sense to me. Okay, now what was the next example?
P and R.
I had to add P and R, right?
Yeah.
So adding P and R means I had to add A, B, C, D plus I, J, K, L, M, N. And what did we say that was?
Undefined.
It was undefined. In other words, it seems to me like these two objects, they seem very abstract, but one thing I do know, I can't add them if they're different sizes. Now in the background I know, oh, that's because they're really functions and the dimensions don't match up. The output dimension of this one is not the same as the input dimension of that one. But when you're just looking at it in this notation, it's easy to see that like that, right? It's a different size, right? There are 4 numbers here, there's 6 numbers there, can't add them. Because my definition for addition, the thing that makes sense is to add corresponding entries. There's no corresponding entries here. So this, undefined. So it turns out, for objects that look like this, in order for addition to make sense, the objects have to be the same size. Let's continue. What was the next thing we looked at? P of R. Now, I'm going to make the assumption that composition is really important and is something I'm going to be doing all the time. So again, because I'm lazy, let's not write the let's just write the P right beside the R. It's always going to be assumed I'm doing a composition whenever I write that. So that basically means I am doing this. Did I do P of R or R of P? Well,
R of P. Oh, POR.
You did both.
yeah, which one did I do first? I kind
Yeah.
of wanted to like, I don't know, I did one of these, right?
Yeah.
Plugging R into P. This is the last example I did, so I think this is actually D.
This is.
That's
That's you should have
Yeah,
done
the P of
undefined.
P of R1 was undefined, so I don't know if that's the example you're trying to do.
You should have done undefined one first.
I showed you the undefined one first,
Yeah,
right?
that one.
So
That
would
might
that
be-
be,
That
P
was
of R
undefined.
was the undefined
I
one.
think it was R of P, yeah. P of R, yeah, that one's undefined one.
R of P was the,
P of R is undefined.
yeah.
P of R was undefined, R, I keep
P
forgetting my
plus R was
notation.
undefined.
Okay, so we did P plus Q, which I'm adding the 2 by 2 with a 2 by 2. Then we did P plus R, in which we attempted to add the 2 by 2 to the 3 by 2. That didn't work. Then we did P of R.
Yes.
Is that right?
Yes.
Yeah, so R of P should work.
Yes. That,
Okay.
this one's C.
Okay,
Yeah.
so that is C. I just wanted to line up so you guys can make the comparison easy. Okay, so I have this guy here, M, N. Okay. Now what did we find out about this one? Undefined. Right? Now it's not exactly clear, if I just looked at this notation without knowing the background interpretation, knowing there were functions, it's probably not going to be clear to you why is this undefined. But we showed that it was undefined because if I interpreted these as functions, this one can't plug into that one. And I want to make an observation here, which when I do the next example, you're going to see. I'm going to take the convention of describing the sizes of these guys, which I mentioned over there briefly. I call this a 2 by 2, and I call this a 3 by 2. So I'm going to be naming these objects based on how many rows they have and how many columns they have. So this has 2 rows, 2 columns, I'm going to call it a 2 by 2. This has 3 rows, 2 columns, I'm going to call it a 3 by 2. Okay? So this is the size of that guy, this is the size of that guy. Didn't work. Okay, let's do the other example. In D, we went the other way, R of P. This was I, J, K, L, and N. And this over here was A, B, C, D. Now, on the surface, these notations don't look that different. I pretty much just switched the order. But somehow this order worked out. And it actually gave us an answer, right? And here's something you're going to notice that is a shortcut for that answer. Notice that the X component, if I took the first row here and dot product it with the first column, I actually got the X component for the answer. Like I'm going to do that process, I'm going to write it down, compare it to what we did before, you're going to realize that all the coefficients line up perfectly. If I take A times I plus C times J, over here, I'm going to take B times I plus D times J. Then for the second row, I'm going to take A times K plus C times L. Then I'm going to take B times K plus D times L. Now I'm going to take A times N plus C times N. Then I'm going to take B times M plus D times N.
Real quick, can you do that again? Actually, no,
I'm think of dot product, right? When you dot product one vector, dot product with another vector, it becomes you multiply these two, and you multiply those two and add them together.
Yeah, oh, okay.
So it's like I'm dot producting the row vector with the column vector. So if I take this dot that, I get this. Take this dot that, I get this,
Okay, okay.
and so on and so forth.
Okay.
Compare this to the answer we got for the thing. You'll notice that in the first component, this was the coefficient of x, that was the coefficient of y. In the second component, this was the coefficient of x, that was the coefficient of y. In the third component, this was the coefficient of x, that was the coefficient of y. I wrote it with a notation of multiplication because it's superfluous to write it because I'm always going to think of it as multiplication, as a composition, really. So what it says here, if I multiply these two objects, this is the process by which the multiplication should work. Now, when I told you how to add two things, it seems to make complete sense. Yeah, you add the corresponding components. But then when I tell you how to multiply two things, this weird formula happens. Why did that weird formula happen? Because they're functions. Sure, they look like just rectangular array of numbers, but in the background, they're actually multi-dimensional functions. My definition has to be consistent with the fact that I'm taking a composition of functions. So when I talk about multiplying these two objects, and I give you this weird definition that seems to come out of nowhere, it's not that it came out of nowhere. It's that the context in which I'm working in is in the background, I'm thinking of them as functions. So there will be times throughout this course where I'm going to give you definitions. I'm going to say, okay, if we want to do this, this is going to be it. And to you it's going to seem, oh yeah, that's obvious, or yeah, that makes sense. And then there are other times I'm going to define things and you're like, This gives that, and you're like, what? Why the hell would that be true? And the truth is, ultimately, you can always trace it back to some manipulation on functions. So ultimately, these things are what we call matrices, and they're really representing functions. So when I'm manipulating matrices, when I'm manipulating these rectangular arrays of numbers, I'm really manipulating functions. And so any rule that applies to these guys have to be able to ultimately apply to functions. Okay? And so that's why some definitions might make obvious sense while some definitions might not. And it's not because I'm just randomly giving you definitions. There's a context, there's a background, there's a reason why the definitions have to be this way. Right? So me just saying, oh, let's dot product this by that. And you're like, why would that be the definition? Well, I showed you why earlier. Okay? So this is also, consider this a warning, an admonition. Don't consider anything I tell you in this course, no matter how tempting it is, don't consider it as obvious or crazy. It's neither, right? So if I define something for you, so it was like in the first class when I told you what a vector space was, and I wrote down 1 times u equals u, and you're like, yeah, no duh, why would you need to tell me that? That's obvious. Is it though? Is it really? Because there are areas in mathematics and objects you can deal with where that is a false statement. It just depends on the context. What do you mean when you write down 1 and that? Because in context, me writing down this really means a composition. I just didn't write it. The interpretation of the objects we're using matters greatly. And so there's really nothing that's going to be obvious or crazy. It really depends on the context. It's just a reality. It has to be that way because of the context we're working in. I also want you to notice something else. If I use this naming convention, what is the size of this? This is a 3 by 2. What is the size of this? 2 by 2. Now, let's pay attention to some patterns here. Because we're mathematicians, we're all about finding patterns. What does this how can I interpret this? So P I'm making equivalent to a 2 by 2 matrix is what I'm going to call it. But what was P? It was a function from R2 to R2. It went from a 2-dimensional space to a 2-dimensional space. It seems that these numbers that I wrote down have something to do with dimension. But how? What is the 2 and what is the 3? Remember, I'm talking about the number of rows. Here I'm talking about the number of columns. R was also a 2 by 2 matrix. And R was from R2 to R2.
R was a 2 by 3.
Q. R was a 3 by 2 matrix. And that guy went from where to where? So this is the guy that's going to, this is why I gave you an example with a 3 by 2, for you to now be able to see the difference, what these numbers actually mean. Where did R start?
2.
At 2, and it ended up in 3. What do you notice about these numbers? There's the 3, that's the 2. The 3 is the number of rows. The 2 is the number of columns. Right? In other words, what can I say the number of rows is equivalent to? And what is the number of columns equivalent to?
The dimension of the codomain.
Dimensions of the codomain. The number of rows in a matrix is equivalent to the dimensions of a codomain. Number of columns is equivalent to dimensions. By the way, this word dimensions is something we're going to have to define in detail. It's kind of vague at this point. You have an intuitive understanding of it, but we're going to need to get a really specific handle on that word. But That's chapter 4. When we get to chapter 4, we'll learn what dimension really means. But this is the dimensions of the domain. Okay? Now, let's look back at these numbers. Sure, I wrote a rectangular array of numbers, but what I really wrote down is a function that went from a two-dimensional space to a two-dimensional space. Here I wrote down a function that went from a two-dimensional space to a three-dimensional space. So notice here, this function has two-dimensional inputs, the output was three-dimensional, but then I tried to plug it into something that's two-dimensional. The fact that these two numbers are not equal was the problem. Here though, that didn't actually happen. The input was two dimensions, the output is two dimensions, but the input of the function that I tried to connect it to is also two dimensions. These numbers are the same. Great. Now let's look at our function r of p. Where did it start and where did it end? We know that it started at R2 and it went all the way to R3, right? So it means that if I take this matrix interpretation and extend it to R of P, what should I expect the result to look like? RP must be a 3 by 2, right? Because it started at a two-dimensional space and it outputs in a three-dimensional space. But what is R of P? It ends up being a 3 by 2. Right? So, what can you take from that pattern? Notice that 3 is the guy outside here, 2 is the guy outside here. Right? So here's what we're going to be able to say for matrices. Later on, I'm going to give you the definition of what it means to multiply two matrices, and I'm going to give you a condition for when that can work. And I'm going to say, you can only multiply two matrices if these two numbers are the same. The result will be those two numbers. Well, that's pretty arbitrary. Actually, it's not, because that's the domains of, the number on the right is the domains of inputs, while the number on the left is the domain of your output, right? So it's not arbitrary at all. It's a matter of fact, it had to be that way. Okay? So when you start to understand the context in which we're working in, a lot of definitions now that seemed crazy, you're going to be like, oh, well, that had to be the case. How could it be any other way? Like, that's the interpretation. It's a function. Yeah, of course it's going to be a 3 by 2, right? So in other words, if you can write down the size of two matrices, you know you can multiply them if the inner numbers are the same. And when you finish multiplying them and you get the answer, the outer number should tell you the size of the answer, right? Because if you take a function from a two-dimensional space to a two-dimensional space, plug it into a two-dimensional space to a three-dimensional space, then the input must be 2, the output must be 3, so you must end up with a 3 by 2. Okay. So addition seems to make sense. Add it component-wise. In order to be able to do it, they have to be exactly the same size. In meaning, this description must be exactly the same for both things if you're adding or subtracting. If you're multiplying though, the numbers have to kind of match up this way, and it's really because the numbers have meaning. There's an interpretation in the background on these numbers. So it's not just, oh, it's a nice pattern, it's very poetic that these two are not, no, nothing to do with poetry. It has to do with composition of functions. I'm taking this function and plugging it into that function, right? And the resulting function is the guy that cuts out all the middlemen. It goes from the beginning here to the ending there. Okay. Did you have a question?
No, I just don't know. It makes sense the way, yeah, it just makes sense.
Okay. So things will seem simple or arbitrary or obvious or crazy when we're writing down matrices, but that's because the notation we're using is really just a compact notation. We're just cutting out all the extra fluff that we don't want to write down. So a lot of the meaning might get lost on you, and a lot of the definitions, therefore, might just end up being, oh, why did you have to tell me that? That was so obvious. Or that's crazy that that's a definition. Why would you define it that way? right? Neither one is the case. There's an interpretation behind it. So from now on, you can kind of, in the next 2 chapters, chapter 1 and 2, we're going to be doing a bunch of things, and at some point I'm going to be giving you a bunch of theorems, and oh, this is how matrices work, and this is what if you do with a matrix, this is what happens, and blah, 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 blah. And you just should have the idea, I would like you to have the awareness that really why things had to work out this way is because they're really functions. And whenever I see a multiplication, it's really a composition. Whenever I see a composition, it's really a multiplication. And another thing you can look at here is that I want you to notice that when I had RP, was not the same as PR. Right? Did you notice that? The compositions obviously don't work in the other order. Right? So, usually when you go into like matrices, a linear algebra class, and the teacher will say, oh, you know, matrix multiplication is not commutative, so this is not the same as that. You're like, what? No, but all the way from when I was in preschool till now, they told me that it doesn't matter what order you multiply. The thing is, it's not multiplication, it's composition. So because you can't plug things into either way, it can't work the other way. So therefore, this might be something you would have taken as an obvious fact. It turns out when it comes to matrices, it's not true. You cannot multiply in any order you choose. In fact, as we've shown, things can get as crazy as, this can give you an answer, but that one isn't even defined, right? It turns out they can both be defined, but they just give you different answers. That's possible. But it's also possible for one to give you an answer, the other one doesn't even make sense. So that's the case, right? And so that's another thing I want you guys to be aware of is, and this is especially why we went through logic and I told you the importance of reading carefully and doing this stuff. There are times when I'm going to tell you things, and it will be a habit for you to assume something else. You have to pull that back. You have to understand, we're not dealing with real numbers. The same rules don't apply. We're dealing with matrices, which represent functions. And so it's different. So don't assume that something that looks obvious on paper is really obvious or not, right? And be careful of what you start to assume based on what I tell you.
Is it possible to equal the same number? Or that's
It's
not-
possible, but it's not, it's strange. Yes?
Are there other like common uses for matrices other than functions?
Yeah, there are tons.
Hmm.
But the matrix theory is basically doing
Oh,
this.
okay.
But matrices are useful for just recording information and organizing it anyway. But from a mathematical theoretical standpoint, this is generally the interpretation that we're thinking about. And there are interpretations that we layer on top of this. But for example, if you're doing like in computer science, you might take a different interpretation on this. Right? So if you looked at, for example, Google's early PageRank algorithm, you realize that it really was focused on matrices and something that we call eigenvalues and eigenvectors, which we'll talk about in chapter 5. But they took a different interpretation of what these matrices mean. Right? The numbers were really the probabilities of hitting a certain website. Right? And so they weren't thinking of functions, they were thinking of what are the chances that someone would click on this website if they search for this term. Right? And they threw that interpretation on it, and then they used linear algebra to come up with this ranking algorithm that ultimately made them the #1 search engine. Right? It was linear algebra that allowed them to do that. But yeah, in our interpretation, matrices represent functions. And by the way, not just functions, I've been saying functions, but specifically linear transformations. A matrix will represent a function that fulfills those two properties that I mentioned to you. So you'll notice that when I was describing P, for example, I used AX plus BY, CX plus DY. Notice that I didn't just throw in another constant that had no variable attached to it, right? Why? Because that would mean it doesn't pass through the origin. That would mean the sum rule or the scalar multiplication rule would be false. It has to be just something that can be written as the coefficients of variables with no extra constant that's not attached to a coefficient in such a way that it's linear. So really, if I throw a square in here, I can't really use a matrix to represent it anymore. Right? It's a whole different theory. That's like differential geometry and sorts of things. Okay? So I just want you to be aware of the background of how we're thinking about matrices so that half as a warning, but half as just a way for you to get a grasp on the theorems and the rules that we'll be talking about. Here's another thing that we can look at, which is going to be important in chapter 4 and 8. So P of xy, we realized this was ax plus by cx plus dy, right? And ultimately we kind of wrote this down shorthand just by looking at the coefficients. But in light of what we spoke about with matrix multiplication, I want you to be aware you can actually think of this as another way. Right? According to the rule for matrix multiplication, which I'll define for you in greater detail very soon, next class probably, I could think of P of xy as the following. Times the vector xy. Right? Notice if I take that rule of dot product in rows by columns, I would end up with this object. Also notice this is a 2 by 2, while this is a 2 by 1. The middle numbers are the same, so I know that this makes sense to write that down. And moreover, the process by which we use the composition of functions makes it equal to this. In other words, you might be thinking, okay, in general, how do we think of a matrix as representing a function? This would lead to, if f of x is a linear transformation, it can be written as A times some vector x, where A is a matrix. Right? And the fact that I can conceptualize a linear transformation as a matrix times a vector is very convenient. And then knowing facts about the matrix that's in front can tell me facts about the function itself. Yes?
Which one's the matrix and which one's the vector?
Well, they're both matrices technically, but if you only have one column or one row, they call it a vector. So if this guy has one column, so technically we call it a column vector. If it had one row, we call it a row vector. But even the word vector is something very general. It doesn't always mean like objects in Calc 3 that you're used to. Like, a vector is defined by the 10 properties that I gave you in the first lecture. Right? And so, by the way, to use that definition, I can think of any matrix as a vector itself, because matrices actually fulfill all those 10 properties that we spoke about. But we'll realize that in a bit. So one thing is, these guys really represent functions, and they're linear transformations, and it turns out, based on what matrix multiplication means, I can express any linear transformation as a matrix times a vector. So that kind of tells me I can study functions by studying matrices and vice versa. Right? So that's a very powerful theoretical thing. So a lot of times you want to prove things about matrices is because you can think of them as these special functions, and so anything that works for functions has to work here. Right? And so that even sort of tells you a kind of existence proof. Right? So you'll talk about things like, so that interpretation, for example, is something that would tell you that in the land of matrices, for instance, something like division is undefined. Right? It's impossible to define division for matrices. There is no division operation. Right? You can't divide a matrix by another matrix. And why? Not all functions have inverses. Right? Because to divide is to like undo a multiplication. But if the multiplication represents applying a function, you're not always able to undo it. So there's no way to actually completely define a division operation. So in the land of matrices, division doesn't exist. There are some functions that do have inverses, some that don't. Therefore, we will see the concept of the inverse of a matrix, but it's not always applicable. It will only apply to certain matrices.
Are those the bijective ones?
They would represent bijective linear transformations, but we will describe those properties in terms of the size of the matrix and certain properties on the matrix. Right? So all these things, they're really piggybacking. A lot of these things that we're doing and guesses that you can make will be based on the fact that you're interpreting matrices in terms of functions. Right? So that also gives you some existence proofs. If you know something works with special functions, and you can always assume, I know it works for matrices somewhere, so it's a worthwhile journey to figure out how it works with matrices, right? If I know it doesn't work with functions, I'm not even going to try, right? So it helps you in that situation, right? So I might ask you, does every matrix have an inverse? And you'd be like, no. Why? It represents a function. Not all functions have inverses. Yeah.
Is that backwards compatible? Like, if you were to give me that f of x can be written as a sub x? Like, so I don't know if that's like remember the thing?
Yes, yes, it is.
Okay.
Right, and we'll have to tell you that.
Mm.
We're going to talk about equivalence, but that I would have to tell you about another special type of function called an isomorphism, which is another kind of bijective linear transformation. Okay, so that's another thing that I want you to keep in the background, that linear transformations, the special kinds of functions that I described in lecture 1, can be interpreted as a matrix multiplication. And therefore, I can talk about functions, these kinds of functions using matrices, and I can talk about matrices using these kinds of functions, and they are somehow equivalent. So if something works with one, it should be able to work in the other. And that's a very important idea, by the way. Let's talk about my watch literally stopped working in the middle of this lecture. I thought I had more time than I have. I have 5 minutes. Can we do what I wanted to do in 5 minutes? 4. Yeah, I'm sure no one's counting. Okay, so to kind of go back to what Leo was saying, let's actually put another interpretation of these matrices for a little bit. So let's look at this guy, A, B, C, D. But I'm going to do an interpretation here. Let me look at this guy as a vector and that guy as a vector in their own right, right? So I'm going to think of this as in, let's say it's in R2, it's just a 2D vector. And this is in R3, this is another 2D vector. Two-dimensional vectors. Okay. Let me just draw a little picture. This is what they may or may not look like. But it's just to illustrate a point. Okay. Let me draw the vector AB. Right, this is the vector AB. Which means to get to that point, the terminal point, what is this?
A,
That has to be A. What is this?
B,
Let's draw the other vector. This is the vector CD. Right? Which means what is this? And what is this?
D.
D. Okay? What do you know about resultant vectors from physics? Remember how to find a resultant vector? Like if these two guys are forces and they're pulling you in opposite directions, how do you know where the object is going to move?
Looking tips to tail.
Right. You create sort of, essentially, you create a parallelogram. You add the vectors on one tip. And the resultant vector is the guy that goes all the way here. Okay? Now, that's a whole other ball game. But what I want us to focus on for a little bit is the parallelogram itself. Let's focus on this parallelogram for a little bit. What is the area of that parallelogram?
the magnitude of AB cross CD.
There's no cross, it's a 2D vector.
Oh.
Let's actually work it out a little bit more elementary.
Are you asking?
Huh?
Are you asking what it means, the area, or like how to actually get it?
No, the actual formula for the area.
Couldn't you just
Space times
solve
height.
it as a triangle and then double it?
Sure, you can do it anyway. Let's actually do it. Hopefully we'll be able to do it very quickly, right? So we have this, where this is A, that is B, this is C, that is D. What is this? And what is that? What would this point be here?
A plus C.
A plus C, which means the length here is C, right? And so what I'm going to do is I'm going to have this idea. I'm going to find the area of this parallelogram by finding the area of this huge rectangle, subtracting the area of these guys. Let's actually do that. So what is the entire length here? B plus D. And the entire length here is A plus C. So I'm going to say the area is going to be equal to A plus C times B plus D minus, let's start subtracting things. What is the area of this rectangle here?
AB.
Huh?
C.
Oh, C, B.
Huh? BC? What is that guy?
CB.
It's also CB, right? What about this triangle here?
A times
A,
Yeah?
AC times
A, B.
Half A.
Half AB, half base times height. To remember our. Okay, what about this one here?
Same.
Same.
Hmm?
That's the same.
This one here?
That's D.
Huh?
That's,
Half DC.
The height is,
D.
C.
yeah, well, this is C and that is D, right? So it's what, half CD? And that took care of that guy. What about this guy over here? The base is C, the height is,
D.
D minus.
D minus.
The same.
It's D, right? Oh.
DD minus.
so that's half CD.
Yeah.
Okay, let's simplify. AB plus CD minus 2BC. This and this is minus AB. This and this is minus CD. Okay, what's going to happen here?
The AB's canceled.
Just negative 2DC.
Oh, we're not done. AB plus AD plus CB plus CD, right? Right? So now what do I have? AB minus AB,
CB minus
CD minus CD. So I'm left with AD minus,
CB. Oh, CB.
was plus BC minus 2BC, so it's minus BC. So I get this expression here. Now I want you to notice a parallel here. Again, we're looking at patterns. Notice that that's what I get if I do this times this and then subtract that times that. Seems like an important thing. By the way, if I were to alternate this vector, alternate the vectors, I would have gotten the negative of this. So what I would do is it say that AD minus BC is actually plus or minus the area of the parallelogram. So its magnitude gives me the area of the parallelogram. Parallelogram. This expression is an important expression. We call it the determinant of the 2x2 matrix. We'll see some other uses of that expression, many other uses of that expression later on. But it's grounded in a geometrical interpretation. And someone else suggested about cross products. The larger interpretation, if you were to do this in the 3D dimensional model, it was just the magnitude of a cross product of the vectors. And so that would be the larger interpretation, but we can build that up from the two-dimensional interpretation. And we'll stop there. So the point of that lecture was just to give you some sort of context in which we're going to work in. Next class we'll actually start some linear algebra, but in the background these are all of the things that are going on, and we'll start actually doing some linear algebra next time. I'll post some online homework tonight. Basically it's going to be doing the just getting used to the online homework system, so it's like a tutorial I'm going to force you guys to do and get credit for. But we haven't actually done any linear algebra, so I can't ask you linear algebra yet. But look out for that homework, and I'll see you guys on Tuesday.
What does it do?
I'll make it due for Tuesday. So I'll post it tonight or tomorrow and make it due for Tuesday. It's just like, oh, here's how you use this program.